We ended on the biology connection with the fatty acids and referring to the saturated, unsaturated, and the polyunsaturated. The next thing is electrolytes. Electrolytes is referring to the ability to conduct electricity, which is dependent upon your ions being able to split into the parts of positive and negative ions, and therefore being attracted or carrying a flow of energy or a charge. So electrical conductivity is the ability to conduct electricity. A strong electrolyte, the ions are easily separated and can conduct electricity quite well. A weak electrolyte, the ions separate but not as easily and therefore do not conduct electricity as well. And then some substances are non-electrolytes and they don't separate at all into ions and therefore do not conduct electricity. So I have the example of a pickle here. We can take a kosher pickle and we can stick 2 wires into it, plug that into an outlet, and we will see it conduct electricity. The sodium chloride that is in the solution to make pickles readily separates into its ions and enables us to have electricity flowing from one point to the other point. Now, before we used to actually have to take state tests on this, I always included about electrical circuits. It is a reminder that that pickle represents an electrical circuit and that whenever I plug it in, I am closing the circuit, therefore allowing the electrons to flow from point A to point B. Strong electrolytes are going to be soluble salts, strong acids, strong bases. These readily dissociate into their ions. Svante August Arrhenius was one of the first ones who postulated. There were several scientists who postulated about this, but he's one of the first ones we credit with this. And he looked into the extent to which a solution can conduct electrical current and how it depended directly upon the number of ions present in the solution. So the more ions you have, the better it can conduct electricity, and the less ions it has, less it conducts. One of the ones that does not conduct electricity very well, if I compared a saltwater solution to a sugar water solution, the saltwater solution will conduct electricity because it has ions, because the salt, sodium chloride, is an ionic bond and therefore has a positive and negative charge, whereas sugar, C6H12O6 in a simplistic form, it has no charge, therefore no drive for electricity, and does not conduct electricity at all. So there are 2 contrasting examples of a strong electrolyte and a non-electrolyte. Now, if I take that sugar solution and I put that into tap water, it is the tap water that will conduct weakly, very weak, electricity, whereas the sugar water and just distilled water will not conduct at all. So, just a diagram showing the difference between weak and strong, just basically pointing out how readily we can remove a part into the ions. A biology connection. This ability to have our ions flowing from point A to point B actually enables us to be able to move. If you recall back from Ms. Swepson's class or biology class, whoever you had, you have an active and you have a passive transport. And an active transport, you've got to get the ions along the membranes in an order in which you can open the gate and get items through the gate. We also use it in our neurons. Our neurons are also electrically induced charges in which you have ions moving across one to the other by a flow of ions. And also Gatorade. Gatorade is used because you need to replenish the ions for your muscles when you use your muscles a whole bunch. And Gatorade has ions in it that our bodies, our muscles need in order to maintain the active transport of the ions across the membrane. Now, so when we get into the math of this, when we're making solutions, we don't just make solutions as a guess. We actually can do it mathematically. And we still use stoichiometry to perform this. Some things we have to think about is the nature of the reaction, how fast it's going to go, and also the amounts of the chemicals present. All of that is going to relate to how much of the material we have and how strong our solution is going to be. That strength, we call it in normal terms concentration. Mathematically, it's called molarity, and you see me doing this a lot in lab where I called it molarity. I tell you what concentration was. I'd say 0.5 mole of copper sulfate. I put that capital M on that bottle, and that was to tell us how strong that solution was. So capital M is for molarity. It means moles of solute to liters of solution, and we write it as 1.0 capital M, 0.5 capital M. And it tells us how strong the solution is. You have stock bottles in the back that have a strength, and I always weaken those down for you for your safety. Important concept is if I look at these diagrams here, it's just basically pointing out that I'm looking at my solute to solvent ratio, and if that ratio is the same, they have the same molarity. So if you look at the third picture, that ratio between the solute to solvent has changed, and therefore you have different molarities. Just like the bottom one also. But the top two, the ratio between the two stays the same, and that's what we're interested in when we look at molarity. So a lab connection here, some of you have seen me do this when I'm making a solution for y'all. I go and I measure how much of the solid substance I need to get that desired molarity. I go get my volumetric flask, I put a little bit of water in there, and then I put the solution in there and I fill to the line. I mix it up and I make sure that I'm still on that line as I invert the bottle and I make my solution, which is moles of solute to liters of solution.